just want to show you today about factor analysis. Last time we looked at principal component analysis. My goal is just to tell you the difference between principal component analysis and factor analysis. That's all. Okay. One of the things about factor analysis is that, first of all, it's an interdependence approach. In fact, sometimes you need it as a stepping stone to do structural equations modeling. It defines underlying variables, what we call factors, dimensions. And what it does is that it will pick the one that explains much of the variability in the data set. Like principal component analysis, it reduces, condenses the variables that are highly correlated into one. Because if they are highly correlated, it means that they are doing the same thing. For example, imagine that you go to the law court, a husband and a wife. The husband has stolen from the bank, but people don't know. So eventually he was caught. Then the man was arraigned before the court. Then the man was told that, no, the man was accused. Then the man says that, my wife knows that on that day, the 24th of December now, they are talking about, on that day, I was with my wife the whole day. I did not go even to the office. So now they have to call the wife to come and defend the husband. The judge now asks the wife, Antenna, your husband says that on the 24th of December, you were with him the whole day. Is that true? Now, let's assume if that woman is a wicked woman, you know, that kind of thing. If she's like one of the ladies here, I hope you guys are not.
Mercy.
She will look at the judge and say, Judge, please repeat the question. Repeat the question. I am saying that your husband says on the 24th of December, he was with you the whole day. Is that true? Me. This man, I don't know this man from Adam, not even Eve. I was sitting somewhere, this man called me and told me that he's going to be accused of things. So I should just come and down do this stuff. The man is doomed. His alibi, I just given up on. I hope you are not. You know, sometimes there's a lady who said that he told her husband that now you have married me, haven't you? You have married me. Now I will show you that I can really bite. I can really bite. But let's assume that there's nobody like that. Or is there someone like that? Caroline, are you one of those people? No. You are special, aren't you? Yeah,
Doc,
you are a very fresh person.
Doc, she is so.
Hey, Carol, is that how you are? She is. Do you also know her?
Very well, Doc.
You know her very well. I see. Let's assume that there's nobody like that here. And now let's assume she's a good woman. Now listen to the story again. Suppose the judge asks this same good woman now, and your husband says she was with you the whole day. The woman is, oh, of course. We were there the whole day. We took some breakfast in the morning. We went to outside to exercise. We came back and started preparing some wonderful dinner. I was with my husband the whole day. Now, why do you think the jury will not be surprised with that answer? Who can tell me? Why do you think the jury will not be surprised with that answer? So I hope you know what a jury is. Why? Listening.
Look, I think because of the correlation or the relationship between the man and the woman.
That's it, because the two of them are too close. That closeness is called multicollinearity. They are multicollinear. So when the two variables are multicollinear, one becomes redundant. It is as though the other one shouldn't even be there. In fact, the wife shouldn't be there. Because whatever the wife is going to say is the same thing the husband has said anyway. Because they are too highly correlated. Now, that is also what factor analysis likes. Can you imagine that? Factor analysis likes it when the variables are what? Highly correlated. So that he can combine them. That's it. So while regression doesn't like it, factor analysis likes it. So factor will assume that observed correlation between the variables, okay, come from sharing some factors together. Like they share something in common. In this case, the two of them are in love. They share the house together, they share the love together, they share the money together. For example, let's take a correlation between the test scores. The test scores correlation might be connected to shared factors. So you take a factor like intelligence, critical thinking, reasoning skills, reading comprehension. When a person has got all of these, it can all come together to create the test score. So you can put all of these together and then come out with one thing for them, combine it and call it test score. So on the basis of this, we can find hidden patterns. Take note. You can identify hidden, latent factors behind the observed variable. So when you look at a variable like x1, x2, x3, all the way up to xp, and then we decide to combine x1 and x2 into maybe, y, 1. And then we combine all the rest into maybe y2. This combination is as a result of something the x1 and the x2 have in common. But that thing they have in common, you don't see it. But it's there. It's latent. It's unmeasured. It's unobserved. It's hidden. These factors are the reason why it makes sense to combine them. So those manifest variables, those observed variables can be combined because of factors that are common between them. That's what factor analysis is doing, basically. So look at observed factors. They start from x1 all the way to xk. Okay? The manifest, the unobserved, the latent factors, they are epsilon. They are pronounced this way. They are pronounced they are psi 1 all the way to psi m. Guys, listen here, because you're about to develop a factor analysis model. You're about to create a model, and you will always answer a question on this. So the psi 1 is the unobserved factor, okay, for combining certain observed factors. And psi m is the unobserved factors from combining all of those other factors. Now, the key point is this, that the m must be less than the k. Who can explain this? 2 marks for that, if you explain it. Who can explain that the m must be less than the k? What does that mean? M must be less than the k. What does the m here mean? The m is the total number of factors, the latent factors, the factors you don't see, the hidden one. And it must be less than the total number of observed variables. Please remember, when you're dealing with factor analysis, there is no dependent variable and independent variable. They are variables. You don't know which is dependent and which is independent. They are all variables. And we are saying that those variables, okay, the total number of the factor, the latent, must be less than the k. Why? The reason is because if it is equal, then it means that every one of the observed variable will have what? Will have an unobserved variable. Yeah. But remember that the unobserved variables is supposed to be a combination of the observed. So it's possible that 2 of the observed can be combined to get 1 unobserved. Another 2 of the observed or 3 of the observed can be combined. So at the end of the day, the total number of observed, unobserved variables should be less than the number of observed variables. That's it. If you don't understand, you can ask. Now, so the entire data set is made up of common factors and then unique factors. Yes, Augustine.
Doc, please, can you take the explanation again? The m should be less than the k.
So if you look at the observed factors, let's say that observed factors are 6. Okay, 6 different observed factors. Okay, and you want to combine them to create some new unobserved factors. Or behind the scenes, there are some factors that connect some of these 6 factors, 6 variables. These 6 variables are there, but then actually 3 of them can be combined into one. And the other 3 can be combined into one. And so eventually we get to 2 different unobserved. So you can see that the number of the unobserved are 2, but the number of the observed are 6. So what we are saying is that the total number of the unobserved must be less than the number of observed. Why? The M, which is the total observed, the total unobserved, must be less than the K, which is the total observed. Why? And the reason is because if, let's say they are equal, if they are equal, what it means is that the observed variables that are 6 and the unobserved variables are also 6. So it means that there's no need for unobserved variables because each one is having the same number as observed. So each observed, x1 will be psi 1, x2 will be psi 2, x3 will be psi 3, sk will be psi m. So we don't have anything. So what we are saying is because we are combining, when you combine things, they become smaller. So when you combine things, they become smaller. The unobserved has become smaller. It is a smaller one because we have combined observed. Okay, do you understand?
Yes, please.
So when you take the entire data set, it's made up of the common factors and then the unique factors. The common factors, the unique factors. Now, what do these mean? So when it comes to the fundamental theorem of the factor model, you cannot, and you got to know this. You see, when we're talking about principal component analysis, we never spoke about a model. We didn't speak because principal component analysis is not a model. A factor analysis is a model. That's one main difference. So this is the fundamental theorem of the factor model. It says that if you take an observed factor, now let's take an observed factor like, take any observed factor, like salary. You know, your salary is affected by your wage. Your salary is affected by, if you were doing regression, your wage, your experience, your education, your position, and so many things. Now let's assume that these are the variables observed. So you take a variable like your wage. Your wage itself, there are factors that your wage has got some relationship. Oh, sorry. So why did I say salary and wage at the same time? Salary is the same as wage. So let's just take something else. So let's say education. Education. So your education has got something to do with your, your experience has got something to do with your education here. Experience has something to do with your education. So experience has got a factor here. And we'll talk about what this factor is. And it's also got a factor, say lambda ij. And then it's got this psi, which is psi 1. Now this psi 1 is the unobserved. It's the unobserved something that is inside this. Okay, but it is also connected to this, to another variable. Okay, so it is inside the experience, but it's also connected to another variable, say education. This one. So it is common. This factor is the common factor. It is common to experience and education at the same time. This factor is common to education and experience at the same time. So that is this side here. But then it is inside what? Experience. It is inside. So when I take experience and I split it, I will see that thing, that experience is sharing with what? With education. I'll see it. But by how much, what percentage of this element, I don't know what element is now, I don't know. But what is the weight of that thing which education is taking part of? So education might be eating just 20% of this thing, and the other 80% is inside. Experience will be eating just 20%, but the other 80% is inside education. So this very thing is the common factor here. So when I take a variable, and now let me go back here. When I take a variable like x or I, that variable is influenced by mu I. What is mu I? Well, we'll hold on to mu I because mu I is basically talking about something we call the intercept. Anytime you form a regression model, look at this thing carefully. It looks like a regression model, where this is the intercept, and the rest are what? The rest are independent variables, but they're actually not independent variables. Why? Because they are actually not variables you can see. You see, one thing about independent variables is that they are observed. But this one is actually rather the observed variable, but there are some hidden things in it. And the hidden things in it are what you're trying to show here. And one of the hidden things is psi, this one. This psi. This psi, which is all the way from 1 to m, is what is known as the common factors. So it is something that is common to both x1 and another x2 or another x3. That is the common factor there. And again, this our principle still holds. And then I said that, and usually this one holds. First of all, why do I say that m is less than k? And now I say m is strictly less than k. Because it has to be strictly less than k. In other words, m is not just less than k, but it is really, the gap is wide. M is really less than. In other words, the number of the latent factors, the number of the common factors are really less. Okay. So we have identified a common factor, but what is the lambda? I've told you already, the lambda are the coefficients. That is the weight, the importance each common factor gives to the observed factor. The importance each unobserved factor places to the observed factor. So it is the importance of what we call the weight, the importance in which the unobserved factor affects the observed. So when you take a variable like experience, there is something inside experience that is increasing experience. Okay, or that is decreasing the experience. The experience is being influenced by some factor, but the factor is latent. It's latent. But by how much? By how much does that factor, that latent factor, by how much does it affect the observed factor? That is defined by the lambda. So the lambda is sometimes called loadings. Loadings. Sometimes the another name is factor loadings or factor coefficients. So what do they do? The loadings tell you the nature of the linear length, the nature of the correlation, the causation between the common factor that is unobserved and that of the observed factor, which is a xi, whereas the common factor is psi i. Okay. So these two are the most important thing. Now we are left with one last thing. Now get something here. If I take all these lambdas together with the xi's, these ones, All of these things I've highlighted is known as the common factor. Don't forget, it's a common factor. Common factor means what? It means that X has these things that are common not only to X1, but it's also common to maybe X4, X5, X9. So that's why it's common factor. Now, of course, if you have something that is common to people, then you must also have something that is not common to people, right? For example, right now, do you know that some of you have got some things in common? You know some of you have got some things in common.
Yes, sir.
Okay. Now, what do you have in common? I think when I entered this room, I said something. What do some of you have in common? Give me anything that some of you here have in common.
Age. Age.
Oh, there. I'm talking about there's something some of you have in common about.
Same course.
Right?
Same course.
Same course, that's it. Okay. Same course. So all of you are doing multivariate data analysis. That is common. But there's something that is unique to you. Right now, there's something that is unique to you. So who can tell me something he has that nobody else here has, or unique to the person? Yes.
Look, I play rugby. No one here plays rugby.
Very good. Is there anybody
He
here
is
who
a
plays rugby apart from him? Exactly. So he was right. He plays rugby. Nobody plays rugby. Okay. So that is unique. By the way, ladies and gentlemen, this factor here, this variable here, okay, this delta here, that is what is known as the unique factor. Okay, so when you go down here, okay, that's the name. Sometimes we call it the error term. The error term, but it's a unique factor. Is that factor that is unique to the variable x1. And so sometimes we call it uniqueness. And it is something that cannot be explained by the extracted factors. Remember, the extracted factors are those that are coming from the observed. So when you go here, when you go to the psi, the psi has a lambda. The lambdas are the factor loadings, the extracted factor loadings. Now, this very one here is that unique factor, okay, which cannot be obtained or cannot be explained by the extracted factor. So if you go to the extracted factor and you're looking for the interpretation, you will not see the unique factor there. It's unique. It's unique to that guy. He says he's got a rugby it is. Finish. And finally, you have the mu I. The mu I is the expected value of the x. Okay. If there was no, factors, whether it's common or unique, if there was none, then what is left is it's just like the y-intercept. The y-intercept. Okay. So this is what is known as the factor analysis model. Now remember, we've said that xi is unobserved. And because we cannot observe, so somebody might say, oh, but you can use OLS to do this. You can't use OLS. You can't use OLS. You cannot use ordinary least squares to run this model. Because to do ordinary least squares to run this, you need to know the value of the psi. But you don't know the value of the psi because remember, they are unobserved. We know the value of the x because that one is observed. So that one. But you need the independent variables in a normal regression to be able to come out with a factor. So if you use OLS, nada, it's not going to work. What do you do? What you do is a different thing. Okay? So we have to use something called maximum likelihood estimation. Maximum likelihood estimation. This is an exam question, by the way. So you need to use that. When we get to the Excel, the R, you see that that's all we use. Okay. So in factor analysis, there are some few things you got to note clear. Assumptions. No missing data or outliers. We don't want that. Normally distributed variables. You need collinearity before doing the principal component or doing the factor analysis. If you don't get multicollinearity or collinearity, you don't need to combine them. You're just wasting your time. Okay. So you need that before you can actually combine them. The next one is you need a very large data set. A very large data set. That's what you need to be able to do that. And then finally, you need orthogonality. It's just the same as, non-correlated independent variables. So if the independent variables are correlated, you don't want that. Okay. So this is how you have to understand and then do it. So the first thing you got to do is to create a matrix and then come out with the loadings. The loadings are correlations between the common factors and the observed factors. Take note. Note that down. The loadings are the correlation between the common factors and the observed factors. And low correlation will indicate that the variables don't have anything much in common. And high correlation means that they have some things in common. So this is a factor analysis problem. And you solve for the unknown parameters, substitute them back into the model, and then you can find a final result. Now, the result is going to give you a lot of things here. You are going to get correlations, covariances, absolute values between the correlation and observed variances. When they are small, it is unlikely that they share something in common. We said this thing already. Now, let me repeat that. So, in fact, always use correlation instead of covariance. Okay? Because correlation deals with the unit of measurement have already been taken care of. Okay. Then you have the rule of thumb. And this is the question I'll ask you. You see, remember I told you the last time that I'm doing just the theory. So next week is going to be all practical. The first rule of thumb you should notice that if I ask you the question that, is there a basis to do principal component analysis? You say yes. Yes, only if you have at least 8 of the variables having a correlation above 0.3. Note it down. When you have 8 of the variables, 8 of the relative variables having a correlation above 3. 8 of them having a correlation above 3. So at least, as long as you can get at least 8 correlations above 3, you're good to go. Oh, and they must be significant. They must be significant. They must be significant. They must be significant. Number 2, after you have identified that, oh, okay, the correlations are above 3, then determine the factors to choose. How many factors are you going to choose? Well, in principal component, we mentioned something about the elbow effect. And here too is the same thing, but there are other 3 steps you can use. Number 1, check the eigenvalues. If the eigenvalues are more than 1, if a particular variable's eigenvalue is more than 1, then that is good news for that variable. Use the loadings. And then also check the screw plot and the elbow effect of the screw plot. The elbow effect of the screw plot. And then finally use a biplot to see how many variables load onto which factor. You can find 2 things from the variable. You remember when we did the X variable, you can find the common factors, which is called communality. And you can find the uniqueness as well. What is the difference between the 2? The communalities measures how much variance of the original data set is accounted for by the observed. how much variance of the unobserved, of the original variable is accounted for by the observed factors. Now, if you can remember in principal component analysis, communality is always equal to 1. Because what a principal component analysis is doing is that it analyzes all the variances of every variable. No, but this one doesn't do that. Remember, we also said that the principal component analysis is not a model. Factor analysis is a model. And if it is a model, what is a test statistic? We use the chi-square test statistic. The software will automatically use it. And then based on that, you can find the communalities. Okay, you can find the communalities. The step 3 is extract the factor, because now you know the method used. Extract the factors. Okay. Principal components is the most common factor extraction method we know. But the other ones like maximum likelihood, alpha method, unweighted least squares, and then so forth. You can have all of that. Sometimes you can go ahead and do factor rotation. Factor rotation, okay, where the factors are rotated to make them more meaningful and easier to interpret. You can do that. Factor rotation. All right. And after the factor rotation, you can also do, by the way, the factor rotation has to be made more meaningful and easier to interpret. And we should look at the interpretation, properly next time. So this is the most important part. What is the difference between factor analysis and principal component analysis? Everybody is going to give me one difference. Okay. So when I mention your name, you just tell me one difference. Who can, I've gotten people who are ready. So Kumado.
Yes, please. We made mention that FA is a model, but PCA is not a model.
Very good. It's there. It's somewhere there in the notes. So you got that. One can be a will. So say something. Mary, give me one. Just forced to say something.
Please, you said what I wanted to see. That was what I wanted to see.
You have said what he was saying.
Yes.
And the next time, think about 2 things, okay? Yes. It's all about life and death. I guess.
Yes, Doc. We also made mention that because the FA is a model, it uses the chi-square test or something like that.
You are making life easy. This one is called Apple. Yeah. Of course, if it's a model, you're going to have chi-square test. That's true. But there's something else. Come on, Alex.
When you take the PCA, the components are calculated as linear combinations of the original variables. But the FA, when it comes to the FA, the original variables are defined as linear combinations of the factors.
This guy is good. Love that. That is so important. Yeah, that point he just made is a solid point. What else? Of course, there are similarities. You can see them here. So let's go to some of the differences. So the difference number 1 is that PCA produces components, FA produces factors. Number 2, PCA eigenvalues account for all the variance. And it's true, all the variance, but in FA, only the shared variances are analyzed. The unique ones are not part. In PCA, the guy has said this one too. There's no probability, no hypothesis, no test, because it's not a statistical procedure. But in FA, it is a statistical procedure. There's even chi-square that is done. Statisticians like PCA. Social scientists love factor analysis. So these are some of the differences that you can have between the two. Now I have a table of some more differences that you can check later. Okay, between, now if you're actually doing this thing in a software called Minitab, you can only input raw data when using PCA. Okay. But you can input raw data, a correlation of the covariance, you can choose any of them, or you can do the loadings from the previous analysis directly when it comes to factor analysis. Another thing about the difference is that if you have a research, and the research, you only want to focus on the variance in the correlation coefficient, you don't want the error variance, then you are dealing with factor analysis here. That's all you're doing. But if the analysis is designed to account for all of the variance, including the variance found in the correlation coefficient and the error variance, then we are in the world of PCA. Okay. In the world of PCA. Please remember that in principal component analysis, the factors are called components. And in factor analysis, the factors are called factors. Take note. Here's an exam question. So that is what I want you to know when it comes to factor analysis and that of the principal component analysis. Now, what I want to do is I wouldn't want to take much of the time for today because I want us to look at the practical. Now that I've done the theory finish, okay, you can read a little bit more about the theories here. Okay, you can check most of the theories. Next time, we are going to take a data set and we are going to go through a series of questions. And these series of questions are the same series of questions. Well, not the same. The majority of them are going to be the same series of questions that you will get under exam condition, just that the data will be different. Ladies and gentlemen, that brings us to the end of the theoretical part of factor analysis. Now, who can tell me the most important thing here that we have executed today?